In this lesson, we will focus our attention on taking a look at a few of the available preemptive scheduling algorithms that are involved in scheduling. It's important to keep in mind that when we think about working with preemptive scheduling, we're focusing on enabling the scheduler to have the ability to take control of a running process. And so in order for it to do this, it must be able to ensure that it can save the state of the currently executing process so that it can return after the selected process has completed. And so let's take a look at shortest job first with preemption, or the shortest remaining time first algorithm. So this is an important consideration that we should take, in that we want to consider if we have a opportune moment when a process rejoins the ready queue after IO completion. So we want to be sure that we have the ability to estimate the remaining time that is needed to make a preemptive decision. So let's consider the shortest remaining time first scheduling algorithm with preemption. In this case, we have processes that are ready to execute. We have P2, P1, and P2 that are executing with P1 and IO. And we have a ready queue available that contains P2, has a time of 20, and P3 that has a time of 25. And so once the IO is complete, we want to consider what might be available in the ready queue. And in this case, we can focus on P1, and it has a time of 7. P2 has a time of 10. P3 has a time of 25. So in this regard, we will opt to deschedule P2 and schedule P1, as it has the shortest remaining time to complete. And so P2 has 10 at this point, P1 has 7, so we will schedule P1 for IO. At this point, P1 is then complete. And so now we take a look again. P1 is in the ready queue. P2 has a time of 16 for IO. P3 has a time of 25. At this point, we want to examine the ready queue and see P2 has a remaining time of 6. P1 has a remaining time of 7, and P3 has a remaining time of 25. So given this, we want to continue with P2 so that it can complete its execution within IO. And so at this point, P1 is also complete as well. And so with shortest remaining time, first we were able to take a look at the special cases in which the shortest job first schedule is executing for the IO processes that are likely to occur. And so now we can take a look at focusing on understanding how priority with preemption can be utilized. And so in this regards, what we want to do is be able to reevaluate priority on IO completion. And so let's consider our priority scheduling with preemption. In this regards, on the CPU, we have P2 that is executed with a time of 10 seconds, P1 with a time of 7, and P2 with a time of 10. With regards to our IO, we have P1 executing with the time of 10. In our ready queue, we have P2 with the time of 5 and P3 with the time of 8. And so with the IO completion, we have P1 that has a time of 1 remaining, P2 has a time of 5, and P3 has a time of 8. So in this regards, we will deschedule P2 and we will schedule P1 because it has the highest priority. P1 is then scheduled for IO and is completed. And so that's how we could take a look at using priority with preemption for scheduling. Our next scheduling algorithm will take a look at understanding the characteristics that are associated with round robin scheduler. And a round robin scheduling is normally used when we want to ensure that appropriate access is given to all appropriate components within the scheduling environment. And so we want to ensure that each process is able to be scheduled for execution on the processor. And so you want to consider that we have an opportune moment when a timer interrupts. If a processor has used its allocated time quantum, and we give the next process a chance to execute with the round robin approach to scheduling. And so we want to consider that within a time shared environment that there are specific considerations that we have to take into account. Specifically, we're dealing with the scheduler having to assign the processor an appropriate time quantum for execution or a time slice. So this is an additional amount of information that needs to be taken into account. And so when we take a look at our process control block, we have our state type and we have the XPCB and as well as the priority that we need to take into consideration. And so a round robin approach is going to be a preemptive, and it does require a timer to interrupt, a timer interrupt. So when a process starts, it is going to be given a time quantum, which limits the continuous CPU time that it can use. So at this point, we want to ensure that a process is dispatched, that the timer is set to interrupt at the end of the time quantum. And so there are a few things that we need to consider. If a process runs for its full time quantum, then the process is interrupted. The schedule is called to put the process at the end of the ready list. The process time quantum is then reset. And then if an interrupt occurs, the process current time quantum is reduced by the amount of its time quantum it has used prior to the interrupt. So these are some specific considerations that have to be taken into account. And so when we're focusing on a round robin scheduler, we want to ensure that we have our appropriate system parameters, as well as the time quantum queue that is going to be considered. Next, we have our ready queue that contains our list of our process control blocks that are ready for execution. And so these time shared environments are going to ensure that we allow for each process to have a share at the processor. And in this regards, we want to consider that we have n ready processes that need to be executed from the ready queue. So at this point, we'll use our scheduler that will assign the processor an appropriate time slice or quantum unit for execution. And so from this point, what occurs is that we'll be switching from the processes to other available processes in the ready queue based on the time quantum execution. When we're switching between the processes, we're going to be utilizing what is called a context switching time. And so that's going to take into account the values associated for each quantum time slice. And so we'll start with PCB1 and we'll have up to PCBN processes that need to execute. And so one thing that we need to take into account is we want to consider what is the wait time for each of the three processes with the round robin schedule. And so let's consider that we have three processes. We have P1, P2, and P3. And in this regard, we have different bursts that we need to consider. We can assume that we have a order of arrival of the processes being P1, P2, and P3. And we're going to consider that the scheduler will use a time slice of 2. So that means that each of our available processes will execute from CPU and IO bursts as shown. And so we can consider that P1 is going to have a CPU of 4, IO of 2, CPU of 2. P2 has a CPU of 3, IO of 2, and CPU of 2. P3 has a CPU burst of 2, IO of 2, CPU of 4, and then IO of 2. And so based on this regard, we can see that P1 and P2 are done before P3 is done with its final IO. And so a round robin approach using a time slice of 2 will schedule P1 to execute from 0 to 2, and then P2, and then P3, then P1 will execute for 2 again. P2 will only need to execute for 1. P3 executes for 2. P1 will execute for 2. P3 will execute for 2. And then P2 will execute for 2. The IO schedule will have P3 executing, and then P1, and then P2. And then there is a lag and no execution. And then P3 will execute to finish out its job. And so we want to consider what are the wait times for processes 1, 2, and 3. So we have the time for T1 is going to be 12. For T2 is going to be 16. T3 is going to be 10. And so we have execution time for E1 being 2, 2, 2, 2. So that's 8. The wait time is going to be 12 minus 8, 4. For process 2, execution time is going to be 2 plus 1 plus 2 plus 2. So that's 7 minus the 16 for our time. So our wait time is 9. And for process 3, we execute 2, 2, 2, 2, 2. So we have a time of 10 minus our time for execution of 14, or total process time of 14. So our wait time is 4. So W1 and so process 1 and process 3 have a wait time of 4, and process 2 has a wait time of 9. And so here we've been able to discern some of the different components that come into place when we're working with a round robin scheduler. Specifically, we have to ensure that we have the appropriate capability to gain control of the processor to utilize the scheduler. So you want to consider that our timer is needed in order to interrupt the processor for the appropriate time quantum. And so we have an interrupt handler that is utilized by our timer interrupt, which allows for the round robin scheduler to function appropriately. But it's important to also consider that we have our processor that is hosting our user program for the scheduler. And so at any point in time, the user program is going to be executing on the processor. And once an interrupt is encountered, our timer interrupt will need to be utilized in order to take control of the processor. And so this handler needs to be able to ensure that it can save the appropriate context of the program executing. And so the handoff needs to occur with what is referred to as a up call. This allows for the scheduler to determine the appropriate next steps that should be taken for the processor and for the scheduler. And so essentially, we'll have a round robin scheduler that will make use of an appropriate dispatcher, a timer interrupt handler, IO request trap, IO completion interrupt handler, and a process termination trap handler. And so let's consider some other aspects about what is done during execution. So what does what in the operating system? And we want to consider that the scheduler is utilized to run the scheduling algorithm, to get ahead of the ready queue, to set the timer, save the context in our process control block, restore context from our process control block at the head of the ready list, and then return. Our timer interrupt handler is going to make use of the PCB. It's going to mark it as timer expired. And then it will have a up call to the scheduler. Our IO request trap will initiate IO operation, move the PCB to the IO queue, and mark as waiting. And it'll do a up call to our scheduler. Our IO completion interrupt handler will mark the IO buffer completed, move the PCB of the IO completed process to the ready queue, and up call to the scheduler. And our process termination trap handler will mark PCB as halted and freeable. It will do a up call to the scheduler as well. And so with these regards, it's important to keep in mind that our dispatcher is utilized in order to dispatch the head of the ready queue to our processor with the appropriate time quantum is available.